Hey, everybody. Let me get a few more coming in. Sorry. So, people edit chat. Let's see. LaDonna Jordan.
Gomez.
Join. Just join. Let me see what's going on. Okay, Crystal, Kimmy, Tringle, go, Cassandra. Good. So I'm working to get. Okay. Looks like LaDonna's having a hard time getting on. Let's send her a quick chat. Okay. Well, let's go ahead and start. Let's see, before I start saying stuff, any questions from you guys on things? I did give you an extra assignment this week. Everyone got it? Come up with 2 questions you want to ask. All right. So I can call on you at any time and you're going to do that. Good. Okay. I did just finish posting the last grades of the homework. Let's see. So what couple of things so there are a couple of things. Sorry, what is this? So mostly it was pretty good. I did check a little bit for completion, and actually had the AI try to check a little bit for completion. It didn't do a great job. Didn't do a very good job on like actually giving feedback to you. I had to go in and look myself, which is good, but it'd be fun to get something that sort of dealt with some of this stuff a little bit faster. Have any of you tried like running your stuff through the AI and, you know, talking to it, asking questions, see if it helps? I mean, it got me into a whole discussion about representation theory the other day. So, I mean, it can, if you know how to talk to it, it can go and go and go. It knows a lot of stuff, right? I mean, it doesn't know stuff the way we do, but thinks it does. Okay, so Tringle did. Well, yeah, I'd be happy to, you know, one of the things about making it work good is I need people to try it and tell me what doesn't work, right? And then, you know, like if you know you're getting things wrong and it's always telling you're getting it right, that's a bad thing, right? So you need to take care of that. Okay, so good. All right. By the way, remember, it's kind of hard for me to read all the messages that come in at the same time. You're here, so you can just talk if you want. Okay.
Well, I guess to answer your question, Dr. K, I've tried using the AI, and I've tried using it in the sense of like break it down even further. So that's why it doesn't. I hope it does a good job, but I'm using that as a way to like, if I run into a question like how to answer like the question, because I think sometimes the AI gives it extremely condensed form, and I'm wondering like, oh, okay, so let me try to go backwards because the condensed form is too much for me. So I'm trying to like, I guess from that way work backwards from what the AI is trying to do. So that's how I've been using it at least.
Yeah. No, I mean, that's a thing, right? Learning how to use it is a thing, right? Because it's, you know, it's not professionally trained to be a tutor or something, right? I mean, I did what I could making the prompts, but yeah, sure. I mean, when I ask it stuff, it'll say, oh, just do these things. I'm like, okay, I don't know what that means. Tell me what this means, you know, and then it'll do something else. I'll say, what does that mean? It'll do something else. And I'll say, why is that true? Right. But if you do that for a while, it'll, and the thing about math, right? And you all should feel like this, is that when you're done, you should feel like, okay, I know how to do this now, right? I know that I'm right now, right? Because it's not mystery, right? I'm not saying, well, I collected this weird data from a super collider and here's my pictures of it, right? I mean, it's you know, it's stuff where you can check every step of the proof, right? And every bit of the reasoning. And so it's really good practice, I think, for your working on proofs and things, right? It's really good practice for you to run a proof by it, or even complain about its proofs, right? Like there's not enough information here, right? But anyway, it's a thing to do. On the other hand, you turn in your homework and you do DQs. So the thing I was going to say about the DQs is most of the DQs I'm seeing are generally very good. They're almost perfect, right? And so the thing about that is it means maybe you're not asking about the ones that you're struggling on, right? Because when I actually went with your homework, there are certain problems that are missed in the sense of not done, right? And then the two I graded, actually a lot of people, only did part of them or, did like, and that was just by chance. I just picked two. And of the two I actually looked at carefully, maybe they're more like this, but of the two I picked, right? A lot of people had only done like half of them or hadn't quite done them right or something like that. So there's stuff going on, right? So take that DQ, right? Because you want this feedback. You might not like it when I give you feedback saying you did this wrong or that wrong, right? But that's how you learn, okay? And you don't want that feedback all on the exam, right? Because the exams are like 500 points, not 5 points, right? So take the opportunity in the DQ form specifically, if there's problems you're working on that you're not getting and have questions on, right? Ask about those, right? Say, I've gotten to this point and I don't see how to go further, right? You understand what I'm saying? I mean, it's not there's no grade in the DQ form just on correctness, right? It's really, I mean, I could have you do silly things like tell me about your week, right? I don't have to have you do math problems. The reason I'm having you do the math problems is so you can get some feedback from me on doing the math problems. Otherwise, you're going to get all your feedback on the exams, right? And then a lot of you are going to be like, gee, I didn't know I was doing all that stuff wrong, right? So it's really good to take that opportunity in the DQs because you're getting to choose the problems, right? And then ask for what problems you want done. Does that make sense? Hopefully. Okay, good. Maybe I'll say a couple of things quickly about the two problems that I did look at, just because once I look at them, I see some common things. So let me share my screen here. I think I'm sharing my screen with the Blackboard, right? It always does something weird to me when I do this. Okay, you're seeing the screen with the Blackboard, right? Okay, let me try to get everyone in here. Sorry, it's just hard to, the little device doesn't quite do what I want it to do here. Okay. So the two I did, the two I looked at was 2.29. And so this one is one that actually, to be honest, you should have seen before in linear algebra. Oh, someone's got a question. Hold on, don't say. Dina has a question. Dina, what is your question?
Yeah, I'm just like remind you because last time you said at the beginning it reminded me to change the background to be white if we like to print like yes,
okay,
please.
Okay.
Yes, thank you.
I mean, my notes are so the one condition is, and I'm going to have this live right here. If you print them, you cannot use them against me later, right? Because my notes are very sloppy. I know they're very sloppy because my handwriting is very sloppy. One of these days, I'll get an AI that can make my handwriting look pretty. That'll be awesome. Not try to turn it into text, just make it look pretty, right? Let's see. I think probably what I need to do is start a brand new board is what I'm guessing because let me do new. Yeah, new. So it's been a long, okay, so I think that's white on, okay, let me get the color here to be black. There are little dots. Maybe you don't even want the little dots because that uses up ink. Sorry, it's been a while since I've messed with this. It's not that. Where do I change the little dots? Yeah, geez, okay. No, I feel like it has to be here. I feel like it's got to be here. It's got to be here. Oh, there, dotted. So plain, right? So now I'm getting rid of my little dots. So now my handwriting will get even worse. Yay. Okay. Also tell me not to erase while I'm going. And now it's going to also be your job to remind me at the end. Actually, let me, just before I do this, let me try to, how do I save it? Let's save it. Actually, let's just save it with the date. So let's say let's say 0915 Matt 513. Okay. Yeah, just tell me not to erase it. I guess that's the main thing. And then remind me that you want it later, because then I have to turn it into PDF and do some stuff like that. But that's easy. Okay, so 2.29 was the one I looked at, right? And you actually did this stuff when you did linear algebra, right? So there should have been an actual sort of memory about this. So when you were doing, what's one of the reasons that you want to diagonalize matrices? There's an algebraic reason why you want to diagonalize matrices. So you remember back there to diagonalization?
To solve a system of equations?
So not usually to solve a system of equations. Like, I mean, one reason is to find eigenvalues and eigenvectors and things like that. But what is the reason for even wanting to do that?
To find the inverse?
So yeah, it's a lot harder to diagonalize than to just find the inverse, right? So it's not quite that. But suppose you wanted to take a very high power of a matrix, right? So, I mean, here we're going to just remember, I mean, by the way, linear algebra is a kind of algebra, so it is reasonable to look at in this class some. So if I have a matrix that's diagonal like this, right? It's just zeros everywhere out there, right? So it just has things on the diagonal, right? And I take like the 100th power of this matrix, right? I don't have to do a whole bunch of complicated matrix operations, right? And this is really the reason you do eigenvalues and eigenvectors too, right? So, I mean, what does this turn out to be? It just turns out to be d1 to the 100, dn to the 100, right?
So really just to like simplify the math when you work with them?
Yeah, and in fact, diagonal matrices act a lot like scalars, right? If I want to take the exponential of the matrix, right? So literally take the the exponent. So, and you might say, what is that? And so I'd have to go into a whole lecture about what that is, right? But you can basically just take the exponential of the diagonal elements. And in fact, for an awful lot of functions, if I want to extend the notion of a function, say from the reals to reals, to the space of matrices to matrices, right? If I do it on diagonal matrices, then I can just literally apply the function along the diagonal, right? So diagonal matrices are really, really nice for that reason, right? And one of the reasons is this. Now, why is this thing true, right? So what does it mean to be diagonal? It means that my matrix A can be written like this, right? Where that's diagonal, right? Now, this looks an awful lot like the problem, which is 2.29, right? Because what the problem did is it said, I mean, let's just remember that I'm, now in my linear algebra class, I want to compute a to the n. Well, that is s d s inverse to the n, right? Well, what is that? That is s d s inverse s d s inverse s d s inverse n many times, right? There's n of those things there, right? And then you use associativity, right? And you put these S inverses and S's all next to each other. And so those all become the identity and go away, right? And so after I'm done, what I really have here is I just have S d to the n S inverse, right? Now that should look exactly like what we just did in problem 2.29, right? In the homework, right? I mean, I know this is a week ago now, so maybe you've forgotten what 2.29 is, right? But that's right. That's exactly it, right? So I want to take a high power of S. I really just have to take the powers of the diagonal elements, right? And then okay, I do have to do one matrix multiplication or two, depending on how you count, right? So that's not too bad. Okay, so this is basically a proof of that same thing. So let me go back and write down what 2.29 was, right? And so you're in groups, right? So now you're in a group, and the claim was that A, B, A inverse to the n equals A, B, N, A inverse, right? And now this is actually for all N and Z, so we do have to be a little bit more careful here, right? So first of all, why can't I just say this? Why can't I just say, well, this is AN, BN, A, minus 1 to the N, that's going to be A minus N, right? Why can't I just do that? And then I don't know, maybe do some other stuff, but why can't I just do that to start with? What is that assuming? I don't know, maybe even do something like this. AN, A minus N, BN, right, which is BN. I mean, I could do that if these were numbers, right? I haven't done anything wrong if these were, say, rationals or real numbers or integers or something, right?
This is both ways is the same way because at the end they give us the same answer.
I mean, the thing you were asked to show was this, right? I'm saying why can't I just go directly from here to there? Like, what's wrong with? There's something wrong with that. What's wrong with that? I mean, let's do it with 2, right? Let's just say, A, B, A inverse squared, right? Why isn't this just A squared, B squared, A inverse? So minus 1, well, I'll do it like this, minus 1 squared, right? But you might write that as A squared, B squared, A minus 2. I mean, maybe there is something we're actually doing there, right? But that's, why can't I do that?
We haven't proved the identity yet?
No, it's more basic than that. What is this symbol? What does it mean to square something, right? It means A, B, A inverse. I mean, why couldn't you do this with matrices, right? I'm sort of, the part of the reason of taking linear algebra first is so you've been exposed to some of the algebra that comes up, right? So, I mean, A inverse squared is clearly the same as that, right?
Is it because we're assuming commutativity?
Yeah, right. If you're doing something like this, where you're just sort of distributing the 2 across the exponents there, you're assuming that the multiplication is commutative, right? But it's not in general commutative. And in particular, in the case with matrices, which we were looking at as kind of a motivating example here, right? That's not commutative, right? Matrix multiplication is not commutative. So this is just doesn't work, right? In the non-commutative case, this doesn't make any sense, right? So what is a valid proof? Now, most of you did give valid proofs, okay, but this kind of thing did come up. So here is a valid proof, but sloppy, okay, and a few of you did this, and I understand why you're doing this because this makes sense. And it's actually not, it's probably what I would do too if I were just thinking stuff. And I would accept it. I mean, like on an exam, I would accept this as an argument, right? So, if I'm taking A, B, A inverse to the N, right, then that just means I have N many copies of those things, right? That's what that means, right? And now you can use associativity a whole bunch of times, N many times, or I'm not even sure how you would count, right? Somehow you reassociate all those parentheses. The point is the parentheses don't matter as long as you don't change the order, right? That's kind of the point, right? So, I mean, you could sort of formally rewrite this as this. Dot, 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 right? Right, and clearly all of those just become E, right? So they just all go away, right? And there's N many of those things, so this becomes A, B to the N, A inverse. Okay, so first of all, how was I sloppy in doing this? What did I do that wasn't kind of formally correct? And this is good to know in this class because sometimes we really need to do this thing that I skipped correctly. Here it's okay to do it informally, but sometimes you need to be more formal about it. And a lot of you did this right. A lot of you did it carefully, right? So what did you do that I didn't just do? I can sit and be quiet too. Like I said, lots of you did it right. So someone can tell me what you did that I didn't do.
So when I'm looking at my notes, Doctor, go ahead.
No, I was just wondering if we state that A inverse is, or yes, A inverse and A are inverses of each other, but
No, that's clear. That's not it.
So when I'm looking at my example, my work, Doctor, okay, what I noticed first of all, because it was aligned with the way the problem is set up, the inverse is first and the A is second. But what I started off doing was let N be 1. Then I went back and I let N be 2 and wrote it out. And then I went back and showed that what happens if it's 3. And then at that point, I identified that A times A negative 1 is basically multiplying. It is A divided by A, which gives me my 1. And once I do that, then at that point, I'm proving that everything is going to become the identity in the middle, which shows that the left side is equivalent to the right side.
Good. Okay, so you have the right idea. You showed it for 1, 2, and 3, but there's a lot of other numbers, right? And so if you're doing something,
I did K also, though. I showed it for K as well to show that if K is an element of N, then it would work for any integer that's inside.
Okay, but how did you do that? That's the name for what you're doing is what I'm trying to get out of you, right? So how do you do that? If I know how to prove something, it's induction, right? Yeah, you're using induction, right?
Induction. Yep.
Yeah. So I mean, you can do the base case. Here, the base case may be 0. That's a reasonable base case, right? So if I do something,
but if 0, it would be 1. It wouldn't show.
Zero's fine. It's got to work for all n, right? So if I put a 0 here, right, is that the same as this? Right. Well, what is this? Something to the 0 is just E by definition, right? So something to the 0 is E, right? And so what is this? This is A, E, A inverse, but that's just A inverse. So that's just E.
Is 1.
Right? So that's good, right? So the base case is true at 0, right? It's true, right? And then to do induction, right? You say assume. I mean, there's various forms of induction, right? But one way is to say assume that A, B, A inverse to the K, like you can make it to the K step of a ladder. And if you can always make it to the K plus first step, right? So you can make it all the way, right? So assume that this is equal to A, B to the K, A inverse, right? And then prove, right? This is how the induction step works, that A, B, A inverse to the K plus 1, right, is equal to A, B to the K plus 1, A inverse. Okay, so how do we do that? Well, what is this thing? A, B, A inverse to the K plus 1 is A, B, A inverse to the K times A, B, A inverse, right?
And try to substitute whatever we got for the assume when it's like raising to A, it's yeah. So we take that K away and put A, B, K, A to negative, like to the negative 1 power.
Yep, just like that, right? So this is where you're using the induction hypothesis, right? And then so here you have now A, B, and now you do the little regrouping thing, A inverse A. Now, see, there's no more dots anywhere, right? So there's no more sort of sloppy math, right? And so you get that. I'm sorry, this is B to the K here, right? And so now this is A, B to the K, B, A inverse, all right? And that's A, B to the K plus 1, A inverse, right? And so that is using induction. I mean, we sort of ran out of time, and this is what happens in the class, right? Is we run out of time to do much. But last week, one of the things that were sort of covered in chapter 0 was induction, right? So this is an example. This is an example of an easy induction. So in like I said, in this particular case, I'm fine with the ... and this sort of argument that I did here, where I just sort of regrouped, right? There are other cases where that's not going to work, right? You can't just, you have to do the work, right? So for example, the fundamental theorem of algebra, which was one of your homework assignments for last week, right? That one needed to be proved by induction carefully, right? You can't just ... somewhere along the way. Now, are we actually done, right? So what we've actually got here from induction is that A, B, A inverse to the K equals A, B, K, A inverse. And I know some of you know, because you did this right, for all K and the natural numbers, right? And by the way, the natural numbers for me and I'm a set theorist, so I am right, start with 0. Okay. You can call the numbers starting with 1 whole numbers, right? But natural numbers for me are going to start with 0. But that's not really quite what the problem asked, is it? The problem asked to show that this was true for all k in Z, right? So how do we deal with negative k, right? So I've taken care of all non-negative k, right? So if I'm going to take care of a negative k, I can I can take care of like k equal minus s, where s is an n, right? And then I can look at, well, what is a, b, a inverse to the minus s, right? So a, b, a to the k is going to be the same as a, b, a inverse to the minus s, right? And now what is this? Well, this is the same as a. Now, I guess there's a couple of things you could do here. I'm going to do it like this. This is going to be a, b, a inverse to the minus 1 to the s. I could do to the s to the minus 1, right? The order I do that doesn't matter, right? Right? I mean, I'll just write it both. You could do this. Those are both the same, right? Okay. Well, let's just, since this one's the last one I wrote, let's just deal with that one. This is positive. This is non-negative now, right? So we know that this is a, b, s to the a inverse to the minus 1. And now we're going to use something we know about group theory, right? And so what is the inverse of that thing? What is, like, if I have a group element A, B, C, and I say, what's the inverse? What's the inverse?
A to the negative 1.
Be careful. So
It's ABC. The inverse of ABC to negative 1, the inverse is ABC.
ABA.
It would be CBA. C inverse.
Is that what you
B
have
inverse,
written there,
A
ABC?
inverse.
Would it be
C
a different
inverse, B in, yeah, someone said it there, A inverse, right? You got to flip the order around. What was this called in your book? They like giving you funny names here. What is the name of that in the book?
I didn't see that.
Socks and shoes theorem.
Yeah. Was it socks and shoes or shoes and socks? Anyway, socks and shoes, right? I mean, you had a homework problem on it. Right. I mean, so when let's not go into the proof of that. By the way, you can you have the little thing I gave you for tutoring. If you want to have you can book a time with me if you want some, like anything I say that I'm sort of going through and you'd like to ask later, you can always book a time and we can have like a 30-minute session, right? I mean, gosh, if I go and redo all of last week's lesson, we're not going to get anywhere, right? But anyway, when you take the inverse of a product, you have to flip the order and take the inverses, right? So going back to what I was doing up here, right? So when I take the inverse of this thing, this is going to be A. So I'm going to flip the order, A inverse, right? And then B, S inverse, right? And then A inverse, right? So we flipped the order, but that's what it turns into, right? This one moved over there, this one stayed in the middle, that one moved over there, right? And A inverse is just...
I'm not seeing anything happening on the screen since you did C inverse, B inverse. Am I the only one?
Are you guys seeing it?
For me.
Oh,
I can see it. Yeah, I can see.
So Tringle, are you seeing it now?
Yeah, it came back.
Okay. So this is the same as A. B S inverse is the same as B to the minus S, and then A inverse, right? And that's what we wanted, right? So we have this here with the minus S. We have that there, right? So we took what we proved by induction and we extended it to the negative numbers by using properties of inverse, right? Good? Everybody good on that? Is everyone hearing me?
I have a question.
Mm-hmm.
So how come we could, I guess, like distribute that inverse into the A's and the S, but we couldn't before when it was N.
Are you just asking about this part?
No. So before we had when we get rid of the parentheses.
I get what you're saying because of this, right? Because it's a theorem that AB inverse is B inverse A inverse. Always. That's always true, right? That was the socks and shoes theorem, right? That's always true, right? It's not true that AB squared, which is AB, this does not equal A squared B squared, right? You're not distributing it. You're using a different property, using a specific property about inverses. It just happens to look similar, right? So that rule does work for 1 in that sort of, I mean, it works for 1 too, right? A, B to the 1, right, is equal to A to the 1, B to the 1, right? So that's also true, right? Now of course, one thing that's different here is the order flipped, right? So that is a genuine difference there, right? Yeah, I mean, so I mean, this deal about inverses, it's just a theorem, right? That's just a theorem. I mean, just real quick, why is that a theorem? How do you show that, what does it mean to be, how do I show something's the inverse of AB? I just need to come up with something that multiplies to give me 1, right? To give me E, right? Okay, well, if I take AB and I multiply by B inverse A inverse, well, that is, A, and then now you're using associativity. So this is B, E, B inverse, and that's just B, B inverse, which is just E, right? So here's a thing which behaves like A inverse, like AB inverse, right? And so one of the things we know from our group theory stuff, right, is that if I have something that behaves like an inverse, it is the inverse. There's a unique thing that has this property, right, that acts like an inverse. Okay, so I mean, that's the reason that socks and shoes theorem is true, right? It's just always true. Okay, that was 2.29. Most people did that pretty much correctly. A few people made some mistakes there. So
are you saying that if we didn't show the negatives, then we didn't get full credit for it?
You lost some credit, not all credit, but you lost some credit for not taking care of the negative. Yeah, I mean, not much, but a little bit. Yeah. So 3.45 was the other one that I looked at, and that one had 2 parts. And so one part was to show that this thing here, so this kind of less than symbol there means H is a subgroup. of G, right? So that's what that little symbol there means. So we're looking at all the subgroups of G where S is contained in H, right? And so we're defining this thing, and we're saying that this S equals the smallest subgroup of G containing S. That was part A, right? And so, and in fact, you're showing that there is I mean, before you prove this, you don't even know that there is a smallest subgroup containing S, right? So that's part of what you're proving here, right? Is that there is such a thing. And I think most people got this part right. So I mean, the way this is defined is the intersection of a bunch of subgroups, right? And so the intersection of a bunch of subgroups is a subgroup, right? And so you have a theorem in your book that says that, right? But it's also really easy just to think through, right? If I take 2 things which are in this intersection, right? I take A and B in this intersection, in here. Well, then for any H which is in here, A and B are in that H, right? So AB inverse is also in that H, right? But that was true for any of those H's. So AB inverse is in all of these H's, right? So AB inverse is also in this intersection, right? So in other words, if A and B are in this intersection, the set of all H, I'm not going to write out the whole thing again, but that thing up there, right? Then AB inverse is also in the intersection of all those things. Right? And so this intersection, you know, is a subgroup. On the other hand, that is a theorem in your text. You could have just said that, right? The intersection of these subgroups is a subgroup, right? Okay. Clearly it contains S, right? Because all of these contain S. So S is contained in the intersection, right? And it's got to be the smallest, because if I have a subgroup containing S, well, then it's in there, right? So it's got to be the smallest subgroup, right? So, you know, sort of formally you're showing that, I guess, you know, some people I think gave this a name, although when you give something a name, you need to make it clear what you're doing, like call that K, right? And you showed like that S is a subset of K, and you showed that K is a subset of S. And so this is very typically what you do when you're trying to show two sets are equal. You show that each is a subset of the other, right? So that's a common way of doing that. Okay, most of you did something like that. And then in the second part, right? Now here we had a little bit more trouble. So in part B, you're given this other thing, which is kind of like linear combinations of elements of S, right? So you're looking at the set of all these products, S1 to the M1, sk to the mk, where the si's are coming from the set S. Remember, S is not a subgroup. It's just S is a subset of G. That's all you have, right? If we were doing additive notation, right, instead of multiplicative notation, right, then this thing right here would be written as M1S1 plus MKSK. Right? Where what are these MIs? These are coming from Z, right? And so this is looking very, very much like a linear combination of vectors over Z, right? So that sort of reminds you of linear algebra sort of things, right? It's a kind of closure, right? Let's stick with this version, okay? And again, some of you called this thing something. A lot of you called it T. Sort of interesting when so many people pick the same name. And what you want to show is that this T is equal to this. I mean, this is sort of the way you guys kind of attack this thing, right? This is kind of how you attacked it, right? So one thing here. So remember, we already know this is the smallest subgroup. That's part A, right? So it is a subgroup. It's the smallest subgroup. You know, containing S, right? We already know that's true for this thing, right? So it's definitely true that S is contained in T, right? So why is S contained in T? Well, just take K to be 1, right? And M1 to be 1, so that this just becomes S, right? So one of the products you're considering is just the single thing S, right? So for any S, right? For any S in S, this product, S, right, is in T, right? Because that product S is just this whole thing up here where both of those two things are just one, right? There's just one thing, right? So it's definitely a thing there. So S is definitely contained in T, right? Now, why is T contained in S? Right, so again, we're sort of checking those, so that's checked off. Why is T contained in S? Well, you know, all these things are in S. We know are in the set S, right? We know that this thing is a subgroup, right? So it's certainly closed under this product, right? This is just a product of things in S. We know that this is a subgroup, so we know that this thing has to be contained in S, right? Because this thing here is closed under these products, right? So that's also true. So both of those parts sort of need to be there for this one. Good. Actually, now that I think about it, I might have said on some ones that what you said was not quite right. And I might retract that now. So now that because I just did this, because my first thought was I mean, the way I think I did it in my notes, right, is I just looked at this thing. Right, and I just showed directly that this is a subgroup, right? So how do you see that this is a subgroup? Well, you know, you like what is an inverse of something in here? So what's S1, M1, SK, MK inverse? Well, that's a good question given what we just did. So what do I need to do with the product? I need to flip the order, right? And then put the minus signs up top, right? So the inverse of this product is SK, MK inverse, right? S1, M1 inverse, right? And so that is SK minus M1, S1 minus M1, right? But that again is just a product of things from S, so that thing is definitely in T, right? And then if I take, right, is that clear? Right, and if I take two products that are in this thing T, right, and I just stick them next to each other, that's clearly just another big product, which is in T, right? Okay, so you could just directly show that this is a group, right? And so that's a good thing. Oh, maybe I checked this off too early, right? Because I wanted to say here. Sorry, let me back up. Okay, see, now I've got myself. So what two things I wanted to show? S is contained in T, right? And I want to show T is contained in S, right? S is just a set, right? T is the set of all these products. Right, that's the definition. Okay, so this part we did right? So to see that that's true, well, all of these things are in S, are in bracket S, because, you know, bracket S is a subgroup. That's from part A, right? So it's closed under these things, right? What was my argument to say that S is contained in T? My argument was that T was a group, right? And S is the smallest group. My argument was that S is contained in T. That's obvious, right? And 2, T is a subgroup. Right, but that needed to be proved. You needed to prove that T was a subgroup, right? So that's that part we just, like the concatenation and inverse and stuff, right? Just to be clear, how do you prove that something's a subgroup, right? Let's just make sure we are clear on this, right? If I've got H subset of G, what do I need to check to see that H is a subgroup of G?
It has to have an inverse in it.
So everything in H has to have an inverse.
Multiplicative, identity, and inverse.
So not additive, but it has to be closed under the group operation, right? So if H is in
closed
H,
under addition, right? Well,
it's not addition; it's whatever the group operation is. And a lot of the time we're using multiplicative, but we could use something else too, right? So if H is in H and H inverse is in H, so it's got to be closed under taking inverses, right? If H and H prime are in H, right, then H prime is in H. So usually when we're just writing things, generally we use this product kind of notation, right? If it were additive, I'd have a plus there, right? And you did say one more, which is important, and that is you can do this in one of two ways. H is non-empty. That's one thing you could say, or you could just say E is in H, right? So either one of those two things.
Yes.
Right. So you could do either one of those. Is there a way of sort of combining these two? Because who knows the way of combining those two? What could I check?
Called it the one-step.
And so what do you check there? If I take A and B and H, I'm going to check that H is a subgroup. What am I going to check? I need to know for A and B and H, what do I need to know?
If A prime and B prime are part of H prime?
There's no prime.
Is that here. Not a prime? Where? Okay.
No, these are inverses, right?
No, I'm talking about up in the other part.
Yeah, well, here there's an A and B in H. If A and B are in H, what is my one-step test going to be? I need to check that what?
AB equals BA.
That A times B is in H.
Well, that's the two-step test. If I'm doing the one-step test, what one thing can I do?
A inverse, B inverse is in H.
That's too much. AB inverse is in H, right? So you wanna just check that AB inverse is in H, right? For any A and B in H, check that AB inverse in H. Okay, you could check that A inverse B is in H, right? Either one of those two would work. But you don't want to take the inverse of both of them, right? You have to have one of them stay and one of them turn into an inverse, right? You still need to check that H is non-empty, or that E is an H. One of those two things, right? Those are sort of equivalent. You still need those things. Okay. Okay, so that's sort of longer comments about the grading that I did. So any questions about any of that?
Yeah, that's okay. I have a question.
Okay.
Not particularly a question though, like more of a complaint. Because yeah, last week class, I was kind of having I don't know if you saw my chat. I was sending a message that I couldn't hear what you were saying, the question you were asking. And only for me to check my grade like 3 days or 2 days after, and I found out that I was missing 5 marks because I did not contribute to the class. So I've actually been busy. I would have replied the message to you personally, but since I'm in class right now, I just decided to bring it up. I couldn't hear anything you guys were saying until I think like 15 or 10 minutes afterwards. That was when I was able to
Okay, that's fine. I mean, yeah, you may have sent me a message, but I mean, I've checked messages today, but I haven't seen your message yet. So that's
that was
yeah.
I said I would have sent a message to you today, but I've just been, because I even came to class late because we had a meeting at school until 8 p.m. today.
Okay,
So
yeah,
I had to leave, and that's why I'm just bringing it up.
Okay, messages is the right place to bring it up. Okay.
Okay.
Yeah. But any questions about the math right now? So yeah, I mean, if you need to message me about grades, yeah, that's a good place is messages.
Okay.
Any questions about the math right now? Okay, you were all supposed to come with like 2 questions available. You can just spit one out if you want, or I might call on someone. Who hasn't talked? Caitlin hasn't talked. Okay, who else? Someone saved you.
Me, Allison.
Okay, hold on. Let Allison go, then you can go next, Philip.
Okay.
Yeah, go ahead, Allison.
My question is on number 9. This is, let's see, what chapter was it? Chapter 5, number 9. No matter how hard I tried looking at it and figuring it out, I can't figure out. I know I probably should understand it, but I can't figure out the product of the disjoint cycles. I can't understand how it works.
Okay, yeah, that's a good one. Okay, it's chapter 5, number 9. Okay. Yep, that's an excellent one. Okay, so here is what we have. So we have 1 for. By the way, I mean, these should be kind of fun actually. 2 and there's more than one way of doing this, by the way. Maybe we could do it in a couple of ways. 1, 3. Now you got to be careful that I don't get it wrong. So everyone sort of watch what I'm doing, because it is very easy to make a mistake here. So we're going to take this thing and raise it to the 10th power, right? So that's the idea. Taking it to the 10th power turns out to be the easy part. What we really want to do is make this into something that makes it easy to take into the 10th power. And one thing to consider here, let me just put some notation. Let's say this is sigma 1, sigma 2, sigma 3, sigma 4. And for this one, it doesn't say where we are. So let's suppose we are in S6. I mean, the biggest thing I have here is a 6, right? So let's say we're in S6, right? So we're looking at permutations of 6 things. Okay, so one thing is that these are all functions, right? So like this one here, this one that looks like 1, 3, 6, right? What is that in terms of a function? All right, so these are permutations, right? So you've got all 6 things here and all 6 things there. Right, so 1 is going to go to 3. That's how you read this thing. Whoops. Dang it. 1 is going to go to 3, right? 3 is going to go to 6, right? 6 is going to go back to 1, right? So that's how these are working, right? So what happens to the rest? Well, 2 just goes to 2, 4 just goes to 4, and 5 just goes to 5, right? So that's what we have there. Sorry, I've lost my picture of you guys. Let me get you back. Okay, so first of all, is that clear that that's what this is doing? Right, so this cycle notation is describing a function in this way, right? 1 goes to 3, 3 goes to 6, 6 goes to 1, right? So another way of writing that, which is useful, would be to put all these numbers up here and then put where they go to below them, right? So 1 goes to
Doc,
3.
Excuse me, Doc,
Yep.
before you lose me. I see 1, 4, 5, 6, and 2, and I have the problem pulled up on the side. So I don't see where you're getting your mapping from unless you address unless this is like the output and the placeholder that it's holding is. So 1 is going to 1, 4. I don't understand how you got your mapping.
So this is number 9, right? So it's 1, 4, 5, 6, 2, 2, 3, 4, 5, 1, 3, 6, 2, 3, 5, right? So that's. So I'm not sure what your question is. So I've got the problem written down, right?
Yes, at the top, and then I see.
And I'm looking at one little part of it, just so we make sure that we understand what we're doing.
Okay, so you're mapping the 1, 3, 6 onto what? That's why I'm asking.
Oh, that's what I said. The biggest number here is 6. So let's suppose all these things are in S6, right? Okay. So they're all permutations of 6, right?
Okay.
Because the biggest number I have here is a 6. I may as well assume they're all permutations of 6, right?
Okay.
So I'm taking my domain and range to be 6 because those are the things we're permuting. And I'm just saying that this symbol, right? This cycle symbol means this function, right? So I haven't finished writing this, right? But 2, 4, 5.
Okay, so I understand.
So let's just make sure we all understand that.
I was lost. I understand now.
Okay. Now, if I wanted to start with this function and get back to this cycle notation, right, that's also easy. I just say, okay, let's see where, in fact, I'll do it in a couple of ways because it doesn't matter where I start, right? Let's see where 1 goes. Well, 1 goes to 3, right? So I can say that, right? Where does 3 go? Well, 3 goes to 6. Okay. Where does 6 go? Well, 6 goes back to 1. Right. And so that's kind of closed off, right? Now, what numbers have I not figured out yet? Well, 2, 4, or 5, right? So now I would go here and say, where does 2 go? And well, 2 just goes to 2. So that's going to be a singleton cycle, right? Okay, now what am I left with? I'm missing 4. Where does 4 go? Well, 4 just goes to 4, right? Where does 5 go? Well, 5 just goes to 5, right? So this thing right here is writing this function here, right? And then I called that one sigma. Which one was that? It's 0. It's called sigma 3, right? So here's another way of writing sigma 3. Whoops, 3, right? It's like that. And this is a disjoint cycle notation, right? So there's a cycle, 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 right? And they're all disjoint, right? So it's a disjoint cycle notation. Right. And again, I'm just focusing on this one thing. Of course, this thing all by itself is a disjoint cycle notation, right? I was just sort of pointing out that if we had this to start with, right, we could get this guy back, right? And you also don't have to start with 1.
I just want to verify that when you say disjoint, you're saying that because each set is unique is distinctive from the other set. None of them are the same, have the same values inside of them, right?
Yeah, disjoint
so
means
you got 1, 3, they don't intersect with each other. So
they don't intersect.
Yeah. Yes, that's what I'm saying. They don't intersect. So that's what makes them disjoint. I'm just verifying.
So I didn't need to start with 1. I started with 1 because that's kind of the obvious number to start with, right? But when I'm trying to come up with these cycles, I could start with something else. I could say 3. Where does 3 go? 3 goes to 6. 6. Where does 6 go? 6 goes to 1, right? Where does 1 go? Well, 1 goes back to 3, right? So I could have that, right? That's the same cycle.
So
it's written a different way, but it's the same function. Yeah.
Totally understand.
So, if I wrote the cycle as 3, 6, 1, that would be equivalent, correct?
It's exactly the same because it's a function and it's exactly the same function, right? It's this function, right? Does that make sense? So as a function, they're exactly the same.
No matter what way we look at it, it's the same value. Got it? Understand?
not sure who asked that though. Who? I think Dina, you asked that, right? Okay, but your mic went off, or anyway, that's okay. So that's that, right? So now we want to sort of figure out what this thing is, right? And it's probably I should copy it or something. Let's see. It's been a while since I've done this. Here, make a copy. Oh yeah, let me just drag that whole thing down. Wait, how do I copy? Oh yeah. Copy. Sorry, it's been a while since I've done this. Let me see. I would like to paste. Oh yeah, there we go. Okay, so there's a new copy of it. Okay, so part of the point is all of these are functions, right? Sigma 1, sigma 2, sigma 3, sigma 4 are all in S6, right? They're all functions, right? They're all functions, sigma I going from, 1, 2 to 6, right? 2, 1, 2, all the way to 6. And they're 1-to-1 and on to, right? Because they're permutations, right? So all of those are like that. So when we look at this composition, right, we're doing it as a composition of functions, right? So I mean, as a function, right, I can compute sigma 4 of 3, right? That as a function, right? And so where does sigma 4 send 3? Well, it sends it to 5, right? So this would be 5. Just want to make sure we got the objects correct, right? These are all functions going from 1 through 6 to 1 through 6, and they're 1-to-1 and on to, right? That's what these are. Okay. Now, when we compose them like this, we're reading this as function composition, like that, right? So this is important because some things you look at, like if you go look at the Group Explorer and you look at that sum, because it's a useful tool, it composes in the opposite direction. So you have to be careful about that. It composes left to right instead of right to left, right? So we're composing this as a function. So if I'm going to compute, like, let's call this whole big thing. Whoops, let's call this this whole thing, let's call this tau, right? So tau is the composition of these. It's sigma 1, sigma 2, sigma 3, sigma 4, right? Then when I compute, say, tau of 5, right? So what is that? Well, that's sigma 1 of sigma 2 of sigma 3 of sigma 4 of 5, right? There's lots of parentheses there. Right? Well, what was sigma 4 of 5? So that was 2, right? So this is sigma 1 of sigma 2 of sigma 3 of 2, right? And what was that? Well, sigma 3 of 2 just keeps it 2, right? So this is sigma 1 of sigma 2 of 2 because it didn't do anything, right? And then what does sigma 2 do to 2? It sends it to 3, right? So this is sigma 1 of 3. And so what is that? It just keeps it, right? So it's just 3, right? So this whole composition, where does tau send 5? Tau sends 5 to 3, right? So that's the sort of way you compose these things, all right? So just to make sure we're composing correctly. All right, so now what I want to do is like compute this whole, I want to compute the disjoint cycle notation for this whole big composition, right? That's what we want to do. Okay, and there are various ways of doing this. Okay, so let's, let me make this bigger so I don't keep running out of space. So what I would do probably is like this. Again, I would probably just start with 1, right? And say, where does 1 go? Okay. So 1 just stays 1 here, right? And now it passes out of there to here, right? So when I put in 1 to this one, it stays 1. It goes into this one. It becomes 3, right? Then it leaves this one. 3 becomes 4, right? It leaves that one. 4 becomes 5, right? So 1 gets mapped to 5. Right? That means in my disjoint cycle notation, so far I have 1, 5. Right? And so the next thing I'm going to say is what happens to 5, right? So 5 becomes 2, 2 stays 2, 2 becomes 3, okay? 3 stays 3, right? So 5 is going to go to 3, right? What happens to 3, right? That's where you start next, right? So 5 goes to 3, right? So yeah, I mean, maybe let me just do, so I'm developing this cycle along the way. So this is 1, 5, 3 now, and I don't know the rest, right? So where does 3 go? 3 goes to 5. 5 doesn't change. 5 goes to 2. Okay, and then 2 goes to 1. So 3 goes back to 1, right? So this one closes off, right? So that's the end of that piece of the cycle. Yep.
So does that make it cyclic in abelian? Because it will bounce back onto 1 and it's gonna follow the same pattern if we were to continue.
I mean, there's nothing about abelian here. This is a cycle of link 3. So being cyclic isn't a property of an element of a group. It's a property of a subgroup of a group, right? Or of a group, right? So same thing with abelian, right? I mean, these are elements of a group, right? The group here is S6, right? Correct. These are permutations of 6 things, right? So there's nothing to talk about abelian or cyclic here, right? I mean, it is a cycle, but that's different from being cyclic.
Okay, because what I read when I was doing my research is that cycles are all abelian, but all abelians aren't cycles. And I figured that since these are disjoint, I don't know. I'm just checking. I'm just verifying so I don't confuse myself.
I think you're using the wrong word. Cyclic is different from cycle, right? These are cycles, right? Cyclic is a property of a group, not a property of an element, right?
Okay.
There is no cyclic element or
tau is not a
element. No, tau's an element in the group. The group here is S6, the permutations of 6 things, right? That's the group S6, right? Tau is an element of the group. It's not a group.
Okay.
Right?
We'll look at cycle instead of cyclic. Okay.
It's a cycle, a single cycle. Yeah.
That's what I said. It's a cycle instead of cyclic. I had surgery on my mouth. My words aren't coming out clear.
Okay. What do I want to put in next? So I'll let you guys choose. So I'm not done yet. I've got 1, 5, 3. That's part of my decomposition. Okay. So
would 2?
Yeah, 2. Why not?
Just end up
anything not here. Itself. So let's see. So 2 goes to 3. 3 goes to 6. 6 goes to 2. So 2 just goes to 2. Good. All right. So now we've got this 1, 5, 3, and then 2. Right. What do I want to put in next?
4.
4.
4 would be good. So let's see where 4 goes. So 4 doesn't do anything. 4 goes to 5. 5 goes to 6. Right. So this goes to 6. So we have 1, 5, 3, 2. 4, 6. Now, actually, we know we have to be done, right? Because that's all the numbers. There better not be anything else. 6 had better go to 4, right? So that's kind of like a little check to see that we haven't made a mistake, right? But so let's go ahead and compute that and just make sure. 6 goes to 3. 3 goes to 4. Uh-oh. Did I leave something out? 1. Now I'm worried. So sorry, 6 goes to 1. 1 goes to 4, right? So that's what I want. 6 goes to 4. Right. I was about to make a mistake in my check, which is bad, right? Okay. So we kind of knew that this had to close off because there is nothing else, right? And that's kind of the proof that this always works, that we are looking at a finite set. So this has got to stop, right? We're sort of decomposing things into finitely many finite sets. So it's got to stop, right?
I have a question on this.
Yep.
Do we need to keep that 2 in it, or can we just drop it?
I mean, you can drop it for doing computations, and we will when we go to take this power of 10, for example, right? But if we want to talk about its type, which is something that we have to do for some other problems, right? Then I would, and okay, so now we do have something where we can talk about sort of a kind of abelian thing. If we have disjoint cycles, right, then the order in which we multiply them doesn't matter, right? So I can take, so let's just think about, wait, I've got my tau. That is my sigma 1, sigma 2, sigma 3, sigma 4. That was this thing we had up here, right? Now we've just written this as these cycles. Let me call this, oh gosh, okay, go call it gamma 1, gamma 2, gamma 3. This would be those guys. right? Now these I can't reorder, right? They're not disjoint from each other, right? But these I can reorder, right? This is the same as sigma 2 or gamma 2, gamma 1, gamma 3, right? I can reorder these any way I want because they're disjoint cycles. Okay, so that's important. It's really important for computing the order of these things, right? And in particular, it's useful and for some things to write this in this way to keep the 2, right? Because this is of type 3, 2, 1. Okay, and the type, so that's for tau, right? It is type 3, 2, 1. And the type is always a descending sequence of integers, or at least non-increasing. It could be 3, 3, right, or something like that. But it's going to be a non-increasing sequence of integers. And these all need to sum up to 6, right? This is all going on in S6, right? So 3 plus 2 plus 1 is 6, right? And so this is a way of breaking up 6 into a sum, right? 3 plus 2 plus 1 is 6. So 3, 2, 1 like this is a partition of the number 6. Okay, and so any type is a partition of the number 6. So another type would be like 3, 3, right? Would be a partition of the number 6. Can you think of a element of S6 that has type 3, 3? So this is made out of 2 disjoint 3 cycles.
1, 2, 3, and then 4, 5, 6.
Yep, that's
2,
an obvious
4,
one.
6, and 1, 3, 5.
Yep, any 2 disjoint 3 cycles, right? What about of type 2, 2, 2?
1, 2, 3, 4, 5, 6.
Yep. Right. So any disjoint, and what do we call these? Like these 2 cycles are like flips or transposes, right? So any 3 transpose. So you get the idea. I mean, any way of breaking up the number 6 like this is called a partition of the number 6, right? And we're looking at what kind of elements are in S6. We're going to consider all these types, right? So each type is one of these things. Now, the importance about types is we can easily compute whether or not it's even or odd, and we can compute its order once we know the type. Right. So we take this tau, we broke it into this thing. So here I can just say tau has type. What was it? 3, 2, 1. Right. So what is the order of tau going to be? By the way, this is the size of the cyclic group generated by tau, right?
It's 6.
So it's going to be 6 because that is the what?
Least common multiple of 3 and 2 and 1.
Yep, good. Right. So once you know the type of an element of Sn, right, you can just take the LCM of the numbers that are in that type, and that gives you the order of the element, right? And so we know that this. So now we do have a cyclic group, right? Tau is a cyclic group. I mean, the thing generated by the group generated by tau, the subgroup generated by tau will be, it'll have E, which is just the identity, right? Up through tau. So it's got 6, right? So it's going to have 5 elements, right? It's going to be tau 5, right? There's going to be 6 things altogether, right? Including the identity, right? You're going to come back around to the identity. Okay, so it's just that, and while we're on it, when I have a cycle, I mean, it's just sort of covered this little bit of stuff. Like I have like this cycle here was here, like 1, 5, 3. Okay. Can I write that as an even or odd number of transpositions?
Can you repeat that question?
Yeah, so any element of Sn can be written using just transpositions, right?
Yes.
And because you have a theorem that says this, I can give you sort of a nice linear algebra proof, or you can just take it as a theorem. I mean, either way. And in the notes, in the videos I gave you a nice linear algebra proof. So if you go watch that, right, then it's there using the determinant. Okay, but then you know that there is uniquely an even or odd number associated to the cycle, right, which is based on how many transpositions is required, right? So how many transpositions are required for this 153? Even or odd? I'm just right. I mean, I could do something where I just add in lots of dumb transpositions.
Even.
Right? So this is going to be even, right? So in general, like what is one way I could do that? I think I could do this as one. Let me see. I think I can do it as 1 3 1. I think here I can just do it as 1 3 1 5. Right? I think this was like one of your assignment problems, right? You could do something like that, right? So let's just. Oh wait, does that really work? Yeah. No, 3 goes to 1, 5 goes to 1, 1 goes to 3, and 1 goes to 5, right? So that works, right? So these are the same, right? So in general, right, there's going to be this thing I'm going to call the sign. So even or odd, right? The sign of a element of Sn, okay, is going to be as well of a cycle, right? The sign of a cycle, right, is going to be -1 to the order of the cycle. And then you can do plus or minus 1, right? So I think I'll just do -1. All right, so the order of this is 3, right? The order of 153 is 3. I mean, should we check that? Like, we have 153, that's in there. Like, okay, so like, what is the group generated by 153? All right, so it contains 153, right? What is 153 squared? So what does that do? So 1 goes to 5, 5 goes to 3, right? So 1 3. 3 goes to 1, 1 goes to 5, right? So it's like that. All right, and let's just check, right? 5 goes to 3, 3 goes to 1, right? So that looks good. Right, so this thing squared is that thing. Okay. And what's the other thing? What's the next thing have to be? If it's going to have order 3?
3 5 1.
So if this group is going to have order 3, right? So like, again, let me just call this thing. Let me call this sigma, right? So there's my thing. So I'm looking at sigma. I'm saying sigma is order 3, so the elements have to be sigma. Well, it's got to be, E, the identity, right? Sigma and sigma 2. If it's going to have order 3, it's a subgroup, right? It's a cyclic subgroup generated by sigma, right? So the next thing is going to have to be E, right? So if I do 1 3 5, so that is sigma squared, and then I do another sigma, which was 153, right? This is sigma, right? So this is sigma cubed, right? This had better be the identity, right? If it's going to have order 3, right? So let's just check. 1 goes to 5, 5 goes to 1, right? So 1 doesn't move anywhere, right? 3 goes to 1, 1 goes to 3, so 3 doesn't move anywhere, right? 5 goes to 3, 3 goes to 5, so 5 doesn't move anywhere, right? So this is just the identity, which I could just write as, nothing. For groups, we usually write it as Z, right? But something, right? Or I could just write it as this, right? I could write it any way I want as a singleton, right? I mean, those are just nothing, right? Okay. So let's just sort of run through that again. Let's say I have this. Let's say I'm in S8 now, right? I've got this funny thing. Let's say 2 4 7 3 6. Okay, so let's say that this is sigma. What is the order of sigma in S8? Yep, you're saying it 5, right? The order of sigma is 5. what is the sign? So sign, if it's even, it's going to have sign -1. If it's odd, sorry, it's going to have sign 1. If it's odd, it's going to have sign -1, right? So what is sine of sigma? Or if you like, is it even or odd?
Even.
So it's even, right? It's going to be -1 to the 5 -1, so -1 to the 4, which is 1, right? Okay. Okay, lots of goodies there. Okay, so we didn't quite actually finish our problem. Our original problem was to take this awful thing and raise it to the 10th power, right? So we haven't actually gotten around to doing that yet. But we did take this awful thing and write it down like this. So let me sort of pull that bit out. Okay. I did not want all that stuff. Let's try that again. I just want this little bit. Actually, I don't even need that too, right? Let's just pull that out. Okay, so our original tau, which was this long thing, sigma 1, sigma 2, sigma 3, sigma 4, is that thing once we've got it down to its disjoint cycle notation, right? And the problem actually asks us to compute tau to the 10, right? Okay, so now we're computing this 1, 5, 3, 4, 6 to the 10. Okay, now can I just distribute the 10? Can I just say this is equal to 1, 5, 3 to the 10, 4, 6 to the 10? So these are disjoint cycles, right? These are two disjoint cycles. So disjoint cycles commute, right? So if I'm trying to compute A, B to the 10, and A and B commute, right, then that is A to the 10, B to the 10. If they commute, right? We're using the commutative, right? These two are disjoint cycles, so they do commute, right? Doesn't matter what order I do them in, right? So I can just distribute this 10 like that, right? It's going to be important for like problems you have on your final or your exam and other stuff, right? So do you all get that? I see Cassandra, you have a question. Yeah.
Yeah, I was just wondering, like, why do we drop the 2?
Oh, because it's really just it's like writing E.
Oh, so it's just like writing the identity. We just don't need to bother because it doesn't have a transfer.
It doesn't really do anything. Yeah, it's like when you have a group element and you're writing out and you have an E in there, you may as well just get rid of it, right? And now the next thing, we have a little bit of number stuff here. This guy has order 2, right? So if it has order 2 and I'm raising it to the 10th power, what is the 10th power of something of order 2 going to be?
Zero.
It won't be 0, but it'll be E. It'll be the identity.
The identity as it divides
one
without a remainder.
Yeah.
And then this one here is order 3. So what do I look at with respect to 10? Whoops.
1, because it has a remainder of 1.
Yep. So this is order 3. So what you're really doing is you're looking at, 10 mod 3, right?
10 mod 3.
Yep. So that's 1, right? So this whole thing just turns out to be 1, 5, 3, right? So our original tau to the 10th power, right? Which is way up here somewhere, right? This awful thing here raised to the 10th power is really just 153. That's what it is when you're all said and done, right? And again, the way you do that, let's just sort of review how you do that. You take that original thing, you write it down in its disjoint cycle notation, and use the fact that you can distribute this exponent through the disjoint cycles, and then you know their orders, and so you can figure out the order of this final thing, right? Okay. What is this tau, our original tau, is it even or odd? Or even tau to the 10, is tau to the 10 even or odd, right?
Is it odd because its resultant is also odd?
So again, the order is odd. The order is 3, right? But if the order is 3, then this corresponding, right? So the order of this thing, it'll be even, right? Because the order is 3, right? The sign of 1, 5, 3 will be -1 to the 3 minus 1, right? -1 to the 2, which is 1, right? So even. I mean, if you want, you could just literally write, again, this is the one we wrote down a minute ago. This is just 1, 3, 1, 5, right? You could just write it down. So there's 2 things there, right? Okay, we've beat this problem to death, but I think we talked about a lot of important stuff here. Any sort of questions on, I guess, really this aspects of symmetric groups? I guess the other thing I was going to do, I hate to spend the whole day doing this one problem. Let me copy this one more time. Let me grab this. There is another way we could have got that disjoint cycle notation. We could have just figured out what this does like this, right? We could have had 1, 2. I just want to, some of you will do this, and so I just want to say that it's okay. Let's just figure out where each of these things go, right? You could do that, right? And you could say, well, where does 1 go? So, 1 doesn't do anything. 1 goes to 3, 3 goes to 4, 4 goes to 5. So 1 goes to 5, right? Where does 2 go? So 2 goes to 3. 3 goes to 6, 6 goes to 2. So 2 just goes to 2, right? Where does 3 go? 3 goes to 5, 5 goes to 2, 2 goes to 1, right? So 3 goes to 1, right? Where does 4 go, right? 4 goes to 5, 5 goes to 6, right? Where does 5 go, right? So 5 goes to 2, 2 goes to 3, and that's it, right? 3. Good, I didn't make a mistake, which is great. Not yet, right? 6 goes to 1, 1 goes to 4, right? So we could take this tau that we had here, right? This whole tau, and we could just write it in one thing like that, right? And once we have this, we can easily read off the cycles too. So 1 goes to 5, 1 goes to 5, 5 goes to 3, 3 goes to 1, right? So it closes off, right? 2 goes to 2. So that's it, right? And then 4 goes to 6, 6 goes to 4, right? So we could do it like that. So this is another way of doing this, right? So you can sort of choose which way you want. It's like, this is like how do you want to organize it, right? Which one of these 2 ways do you want to organize your work in, right? So that's a different way of organizing it. The important thing is to get the disjoint cycle notation. That's the important thing in the end. Okay.
And this is counted as a full credit if we did this way?
I mean, what you had to do for this one was you had to find the disjoint cycle somehow, right? And then you had to raise that to the 10th power. You weren't going to do that by hand, right? You weren't going to literally take this thing and raise it to the 10th power. That would be a mess. So you have to do something like this, right, to do it. Now, this isn't one I graded, right? So this, but if it goes up on a test, right, you need to do something like this, right? Good. Okay. That's good. Let me see. Let me see what question Philip had. So Philip, you were gonna maybe ask a question.
Yes. My question is actually from I have one from question 4. I have one from permutation group, which is from chapter 4, and then the other one is from. In fact, I have 2 questions. One is from chapter 4 about cyclic groups, and the second question is from chapter 5 about permutation groups.
Okay.
And I think you just answered the one for permutation group using from the question 9 from chapter 5 that you just finished solving. I think I have a very, very good idea of what we're asked to do for that question now. So I think my second question has been answered, but the first one for the chapter 4 for cyclic group, I really want to know why does every subgroup of a cyclic group have to be cyclic?
Okay.
Could you explain the proof in simple terms, and maybe you can just show how it works with Z12 or Z11?
Yeah, sure. So let's just go through it. Let me get my own brain in. So just so we get some definitions out. I've got a group. The group doesn't have to be abelian or anything, right? And I'm going to take an element inside the group. Okay, so let's just make sure we all understand what cyclic is, right? And so then I'm going to look at the this set, the things generated by G, and what this means is it means the set Gn for n element of Z. So by definition, that's what this is, right? And so there's so this thing right here. So there's a couple of things to say about this. This is a subgroup of G. So it's the cyclic subgroup of G generated by little g, right? And why is it a group? Well, because if I take two things and I multiply them together, I get Gn plus m, which is definitely in there, right? So it's closed under the group operation. And if I do G inverse, right? Well, that's also in there because I'm taking negatives here, right? So G. If I take something in there, so something in there would be a Gn, right? If I take Gn inverse, well, that's just G minus n, right? And the identity, right? G to the 0 is E, right? So we have the identity, right? So we've checked that this is a subgroup, right? So this is always going to be a subgroup. And that's what a cyclic subgroup is, right? So that's one thing, right? So now we're in a case. So now the question is, suppose we're in a cyclic subgroup. So we're in G, right? So we're in that kind of situation. And I'm going to take an H, which is a subgroup of G, right? Like that. Let me think. I'm trying to think for the infinite case. Let's see, maybe the same proof works for all. So we have H subgroup of G. Let's take G to the M, which is in H, right? So everything in H is of the form G to the M, because this is a subgroup of the cyclic group, right? Where M greater than 0 is minimal. Okay. It's definitely the case that G to the M is contained in H, right?
Yeah.
Because G to the M is in H, so definitely anything I generate from G to the M is in H. So just to be clear, right, things in G to the M are things of this form. They're things of the form G to the M to the N, right, where N is in Z. Right? And now, so what I want to do, right, is show that H must be contained in G to the M, right? And that would show me that H is uniquely this. So the way I would actually, given a particular H, what I would do is just look for the least power of G, which is in there, and that would be the generator of H, right? So that gives you a pretty solid algorithm of finding those, right? It's not the only thing we can say, but that's certainly a good start, right? So can we see if we take anything in H, take some K in H, not K, yeah. Well, actually, so H is a sub, so take G to the K in H, right? because H is a subgroup of G, the cyclic group, right? So everything has the form G to the something, right? So take a G to the K and H. We want to show that G to the K is an element of G to the M, right? Like that, right?
Yeah.
You buy that? Now we're going to actually just use Euclid's division algorithm, right? So K is equal to QM plus R, right? Where what do we know about R? Is 0 is less than or equal to R less than M. Remember, M was chosen here to be the least positive, right? Okay. And what am I going to get? I'm going to get that G to the K is equal to, let's see, yeah, so I'm not done. Okay, so it's G to the QM
plus R.
QR, right? Okay, but this thing here, that's in here, right?
That's in, yeah, that's it's
in this is a subset. It's a subset of H, right? So in particular, I can get G to the K, G to the minus Q. Basically, I'm going to multiply both sides by that is equal to G to the R. Sorry, I wrote Q. That should be a G, right? G to the R. Right. But what do I know about this? Well, this G to the H, this G to the K is in H. This G to the QM is in H, right? Because it's of the form G to the M to the minus Q, right? And that's contained in GM, right? Which we already know is contained in H, right? So that's in H, that's in H. So this is in H, right? But that means this is in H, right? So that's the main thing, right? That is in H, right? We're really just playing with numbers here, right? And so the point is that this R is less than M, right? But GM, so what was M? M is least greater than 0 such that GM is in H, right? So what is it? GR is in H, but R is less than M, right? So the only option for R is to be 0, right? But what does that mean? It really means that G to the K is actually just equal to G to the QM, right? I mean, this R here is just 0, right? So it really just says that's all you really have, right? So actually a multiple of M, okay? So what's, by the way, why is this true? Why is there a least M greater than 0 such that this happens? This is a good question, actually. I mean, what mathematically lets me say this? How do I know there's any, so maybe there's a couple of things to say here. How do I know there's any M, right? So H is, remember, H is contained in G. There's a lot of things that sort of get swept under the rug that we're actually using here, right? So H is contained in G. How do I know there's any G to the M where M is greater than 0 such that G to the M is in H? I mean, I guess in some sense that's sort of silly, right? Because H is, something's in H, right? So, you know, let's say, I mean, it's not the empties. H has something in it, right? Okay. Maybe I'm using, actually, there's a little subtle thing maybe I'm using here. I'm using that H is not the trivial subgroup, maybe, right? So I'm even maybe saying that H is not just the identity, right? Otherwise, I'm sort of stuck. But if H is the identity, we know what we're doing, right? So it's not an issue. So if H is not the identity, there's something, right? G to the M is in H for some M and Z, right? Well, if M is positive, we're done. Then we've got a positive power of G, which is in H, right? If M is not positive, if M is negative, then G to the minus M is in H, because H has to be closed under inverses, right? But then minus M is in there, right? So what I have is I have this. I have the set of all M greater than 0, and G to the M in H. That set is not empty. There's something in there. How do I know I have a least thing in there?
Say that again.
So what we just showed is we showed that there's some positive m, so that g to the m is an element of H, right? So again, our assumption is that H is a subgroup of G, of this cyclic group G, right? And H does not equal just the identity, right? It's got more than just that, right? So from those two things, right, we get that there is some positive m so that g to the m is an H. How do I know there's a least m, right? In my argument up here, I had to have a least m, right? How do I know there's a least m such that m is an H? How do I know there's a least element of this set? It's a non-empty subset of the integers, of the positive integers. How do I know it's got a least element?
Is it because of the inverses?
No, I mean maybe it's tricky. It's something that came out of chapter 0, right? So it's part of like the preparatory stuff for the class, right? So we had induction, and induction is equivalent to something else called the least member.
The partition thing, the port something.
No, it's not the partition thing. Induction. Least member principle.
Because of the well ordering principle?
Or maybe we call this even well ordering principle, right? Whoops.
Yeah, it was the principle that said every non-empty set of positive integers has a smallest member.
Yeah, and I can't remember if I'm supposed to put an AL or an LE. Now I'm forgetting my spelling at the moment, right? But these two things are essentially equivalent, right? Induction and well ordering principle or least member principle are equivalent to each other, right? So saying that there's a least thing in here that I could have chosen wherever I did that, right? So where did I do that? It's way up here, yeah. Right, I chose this to be minimal, right? That's equivalent to induction, right? It's a fact about the integers. If I have a set which is bounded below and it's non-empty, there's a least member in it, right? So that's called the well ordering principle or the least member principle, and that's actually equivalent to induction, right? And it's also equivalent to the fact that I can't get an infinite descending sequence of integers, going that way infinitely long, right? So there's a lot of things that are all sort of equivalent to each other, right? But we actually use that here. I mean, so we're actually using an axiom of arithmetic, right? In this argument to say that I can find a least thing such that something happens, right?
But Dr. K, quick question. When you got it to where it says K equals Q M plus R at that point, R is the remainder, didn't you try at that point transpose that to, transpose is the wrong word, but at some format, was that some type of modular arithmetic, and we could have found the answer that way?
I mean, it's not exactly modular. It is in a way, but I'm just using Euclid's something. Euclid's division algorithm.
Right. And at that point, can't we just go from there in the same way we would with logs and exponential forms, and just, since all of the bases are G, couldn't we just work with that to find our solution?
I mean, I'm basically arguing by contradiction that R has to be 0, right? I mean, so I don't think there's a way to avoid this part of the argument. You have to argue that the remainder is 0, right? That's kind of what you're having to do.
Okay.
Does that all make sense?
Sorry, one more thing. Can we can we find, like, from that some cyclic group, can we use this example to just really explain that by finding our generators, and let me say Z15?
Yeah. I know what you're saying. Yeah. So I haven't quite answered like the Z12 type question, right?
Exactly.
So that's important, right? So we're here, right? So I've got a so I'm in a cyclic group G, right? I've got a subgroup H. And I think the general setting is like, I know that H is of the form Gn for some n. That's sort of the general kind of setting, right? So that's what's going on in Z12, right? So this is just generated by 1 in Z12. It's generated by 1, right? So that's sort of the generator there, right? And if I take some subgroup of Z12, I know that it's going to be given by something. So I know that H is, say, maybe it's generated by 5. 5's not good. Let me choose something else. Let me choose 10. Let me choose 10. Say generated by 10, right? So I know H is going to be generated by something, right? So that's kind of the setting, right? So I'm in a cyclic group, and I'm looking at a subgroup which generated by some power of the generator of that, right? So that's kind of the idea, right? Okay. And I would kind of like to get the best power, right, for this, right? So that's kind of the point, right? I guess for infinite groups, it doesn't quite make sense. But if it's a finite group, right? So say G had size, I'm using n already, so let me call it K, right? So I know that this is, the set of all E, G, et cetera, up to G, K minus 1, right? And inside there, I've got some Gn, and I'm looking at the group generated by this Gn, right? And I would like to know, like, what is the size of this group inside of this thing, or something like that, right? Same kind of thing here. What's an easier way of representing this, right? Instead of 10, is there some easier way of doing it, right? And so what you do there, right, is you do sort of a similar thing. You say this. You say that suppose the GCD of this n and k, right, is equal to d. Okay, so in this case, up here with Z12, right, I'm saying what's the GCD of 12 and 10? All right, so the GCD of 12 and 10 is 2, right? Okay, so here I'm just looking at the GCD of n and k. So I've got an element, a power of g. My group has size k, right? So we're in that situation, right? And what I want to claim here is that GD is actually the same as GK. In this notation, in this multiplicative notation. In this one, right, 2, right, so I'm going to claim that 2 generates the same group as 10. Right, so this kind of tells you...
Dr. K, where did D come from? Because you got GCD in K, the greatest common divisor. And then you got GD is D. Okay, so you move that over and made that the exponent.
Yeah, I'm saying that if we are in a cyclic group of size k in this case, right, and I've got a power of the generator, Gn, right, and I'm trying to figure out, basically I'm trying to figure out the best generator for it, more or less, right? I'm trying to figure out kind of a canonical generator for it, like the smallest m greater than 0 that generates it, kind of like in that proof above, right?
Yes.
I can take the GCD and I will generate exactly the same thing. Right. So that's what you're doing here, right? Suppose we made this problem harder and we said, okay, we're in Z1024, right? And I've got 56, right? And I would like to know something like, what is the order of the group generated by 56 in the group Z1024, right? I'm sort of doing something crazy like that, right? So what I want to do is I want to find the GCD, right? If you find the GCD of the size of the group and the sort of the generator, right? The thing is, this is like 56. The thing is with the notation with the generator here. Here's where the notation, you've got to get used to this notation, right? So the generator for Z12, right, is 1, right? So I'm not writing I'm writing 10 is really 10 times 1, right? And we want to think of that as like 1 to the 10 if we're thinking about the multiplicative version, right? So this is like here I'm writing GD, GK, it's kind of like thinking about it like that, right? As opposed to D times something, right? So if this G were an additive group, right, this would be, instead of writing G to the D, I'd be writing DG equals KG. Right? Because you're just repeating G over and over, but you're either repeating it adding or you're repeating it multiplying, right? So you've got to sort of you got to be careful with the notation, right? That's all I'm saying, right? So usually when we're thinking about it in general, we use this multiplicative notation. Okay, but the claim is that these two groups are actually the same, right? And so why are these two groups the same? D divides N and K, right? So K is definitely of the form Q times D for some D, right? So GK is definitely in GD, right? On the other hand, because of Bezo's theorem, right, we have that Sn plus Tk equals D, right? D. So we have that G to the D is equal to G to the Sn plus Tk, right? So this is G to the N to the S, and then G to the, and I want to get the right order, K to the T, like that, right? But what is G to the N? G to the N is E, right? So this is just G to the K to the T. But that is an element of G to the K, which was the original side over here, right? So if GCD of N and K is D, then I have the G to the D. The cyclic group generated by G to the D is the same as the cyclic group generated by G to the K, right? So that's the point, right? So in general, so let me just sort of phrase all this again. So if I have a cyclic group G, right, I'm going to change K and N around a little bit. So suppose G has size N, because I like using N for the size of the group instead of the power of the element, right? And I'm interested in what subgroup G to the M is, right? Like which subgroup is this? Well, I know that this is exactly G to the GCD of M and N. Right? So I know exactly how to find sort of the least generator in some sense for that thing, right? Okay, and then once I know that the order of G to the M, the order of this group, is the same as the order of that group. But now this one, think about it, is being generated by this sort of least generator, right? This is clearly the same as the size of G over, you know, how many times can this thing go into N, right? It's over the GCD of M and N, which is just, you know, N over the GCD of M and N. Right, so you know that, right? So I mean, so that's, these are sort of the two main things you use, right? The main thing is coming from this. The main thing is coming from, if I take any power and I look at the subgroup generated by that power, it's the same as the subgroup generated by this power, right? And so that's really useful. I mean, so again, to take some sort of crazy example, you know, suppose I'm in Z 5,404 or 5,046. So I don't know anything about what that thing is, right? And I look at 128, right? I'm interested in like, what is the order of the group 128, or what's the best generator of that group, right? Something like that. So what I'm going to do, and now I'm going to cheat, right? So I'm going to come here. I'm going to say Desmos, and I'm going to say GCD of 5046 and 128. And so it's 2, right? This is the GCD of that thing, right? So let me make sure I can see you all. Okay, so it turns out that the GCD of 5046 and 128 is 2. That's kind of surprising. I would have guessed there would be more that I could divide by, okay? But I can't, so that's what I get. And so what does that mean? The group generated by 128 is exactly the same as the group generated by 2, right? And so you know exactly what the group generated by 2 is. It's 2, you know, it's 0, 2, 4, you know, etc., up through 5044, right? It's all these sort of even elements of Z 5046, right? So you know exactly what size this group is going to be. You just take 5046 and divide by 2, right? So you see what I mean by, like, this is a generator of something. It generates some subgroup H, right? But once we use this fact, we can get kind of a very canonical, nice generator that I understand completely, right? You see what I mean? You know exactly what that generates. And this also tells you why, you know, there's only one subgroup of this size, right? Because it's going to be generated by that thing there, by 2. Right? There's going to be one subgroup of this size. So that's the reason each subgroup of a particular size, the subgroups have to divide the size of the like any subgroup of this will divide 5046, right? And for any particular divisor of 5046, there will be exactly one subgroup of that size, right? And it will be generated by exactly n over that number, right? So you sort of know everything about cyclic groups, right? They're very, very simple in this sense, right? So they're like their lattice of subgroups goes straight down. You got, you know, Z12, what divides Z12, you know, and sort of just go down with divisors, right? So it's very simple. Excellent. Okay. Yeah, so I mean, again, we've only talked about some small fragment of what's actually in this week's stuff. So I'm hoping you're looking through, you know, so just to remind you, right, every week, wait, where did I do it? Yep. Every week I have this posted, right? And so there's a whole bunch of lectures on all of this stuff, right? So, you know, in these 2 hours, we can only get over part of this stuff, right? So just, you know, I'm going to have to, you know, we have to rely on you to ask the questions you want to ask, right? So hopefully you're watching that stuff, reading the text, and, you know, coming with questions. So let me just check one more time. Are there any questions you want to ask now about any of this stuff? So we've got cyclic groups. We've got, I think we see how to find the disjoint cycles for symmetric groups. I think we see how to find the order of an arbitrary element of a symmetric group by finding the disjoint cycles. How do we find whether or not even or oddness, right? If I got sigma 1, sigma 2, sigma 3, right? How do I know if I've got even or oddness in general? Like if I don't, like, you know, 1, 4, 2, 6, 2, 4, 5, 3, 4, 6. Okay, so there's like, maybe it's those 3 things, right? Let's say we're in S6 again, right? Can I just look at these and tell whether it's even or odd real easily? You have to get the disjoint cycles first, right? First, you have to get the disjoint cycles, then you have to figure out even or oddness, right? And do that sort of thing, okay?
Actually,
Actually,
I'm not sure
that chapter 6 is very challenging. The last problem.
5 in chapter 6. Okay. Well, if no one else is asking for anything, let me take a look at it.
It was very challenging when I was reading through it and trying to decipher the vocabulary using explain this word, explain that word, and I just like, let's go to a different problem. Never mind.
I think that was actually when I had written down.
Oh, okay. So I'm going to do it in a slightly explain why this means that odd dn is at most nun. Okay, so let f be a reflection of dn. Explain why the automorphisms of dn is completely determined by the choices for. Okay, so let me do it like this. So the way I usually view the dn, now here I'm going to go into the way I think about these things, right? So dn, I think of generated by these 2 guys, r and f, right? So r rotation. It's a rotation by, you know, 1/nth of a complete rotation. If you're, you know, 2 pi over n, if you're using that, right? F can be any flip at all. It doesn't really matter which one it is, right?
Right.
And it's got these relations. It's got to satisfy Rn equals E. It's got to satisfy F squared equals E. And it really only has to satisfy one other thing, and that is that Rf. So Rf, if you think about it, is also going to be a flip. And so when you square it, it will also be equal to E.
Can you slow down in your speech? Because when you start talking fast, you start writing where I don't understand what you're saying. So did you say F squared or does that say FN at that very first one? You got RN equals E identity. Does that say FN equals identity?
No, squared. The
that's
reflection.
Okay.
The reflections all have order 2, right?
Okay.
So this is a reflection. If I take a rotation and reflect, then the result is a reflection, so it will also have order 2, right? And these 3 relations determine everything about the set, right? So I mean, this one here, right? This RF squared equals E. Let's just think about what that says. It says RF equals E, right? So I can now I can do some algebra. F inverse on both sides, but what is F inverse? It's just F, right? So I can just multiply by F on each side, right? So this will turn to RFRE equals F, right? And then then I can multiply by R inverse on both sides, right? And what is R inverse? So the R's form a cyclic group, right? Right, so the inverse there is going to be R to the n minus 1, right? So you also get this relation. And doing the same sort of thing, you actually get that RK to the F equals FR to the n minus K. Okay, and if you think about that sum, that really just allows you to take any word, so any sort of sequence of R's and F's, and pull them down into just one of these 2 forms, so that all of these things are just ER through Rn minus 1, and then F, RF, Rn minus 1F. So that's really all there is. Those are got to be all the elements in Dn, right? So there are 2 n many elements in Dn. Okay.
So can I just repeat what I think you stated at the top? That's R squared is identity, F squared is identity. Then you got RF squared is equal to identity. And then you broke down the different groups. And each time you got the identity, you changed it to an F. Because you got RF, RF times RF equals E, and then it became RF times FF. And I'm trying to figure out why do I have 3 Fs now? That's all I'm trying to do is
I mean, look, if this was just XY squared equals 1, right? I mean, that's sort of what you're doing here, right? So this is XY. We just don't have commutativity, right? XY equals 1, right? I mean, I'm just doing algebra here, right? XY, X, Y, Y inverse, right? I'm just multiplying both sides by Y inverse, right? We just usually use E, right, for the sort of generic identity in a group, right?
The E's are not what's confusing me, Dr. K, if I may. At that third letter, the third sentence, the third math sentence you have there, you have RF times FF equals EF. And I'm trying to understand where that third F came from. That's all I'm trying. Or is that RFF? That's what I'm not computing what I see. It's not registering.
Okay. Because F equals F inverse, right? So what we have is RF equals, let me use 1 instead of E, okay? So RF,
the E is not a problem.
Okay, so now I'm doing algebra, right? So I'll put the E back. So I want to get rid of the F here. RF. Now I could put F inverse equals EF inverse, right? So I could do that. So that's going to become E, right?
Okay.
So this is RFR. E just goes away, right? This E goes away. So this is F inverse, but F inverse is just F, right? That's what the fact
I'm understanding now. I get it. I see the step that I didn't follow. I understand now.
Okay. So if I take any combination, if I take any sort of crazy word here, like if I do like R5, F, R6, F cubed, R7, something, right? I can always turn this down into something of the form, or, say I'm in D, I go all the way to 7 here. Say I'm in D8, right? So I can get this whole thing down to just some sort of R something F, right? Just using those rules, right? So everything has the form power of R times F or just the power of R, right? So everything has this form.
Okay.
Okay. So when you're asking what determines a map, right? That's going to determine a homomorphism or an isomorphism. All you're going to ask is where to, so see, these are, it's not like a cyclic group. There's not one generator. There's two generators.
Right.
There's two generators and there's these rules, right? To determine a map here, all I need to do is say, where do these generators go? That's what I need to do to determine a map, right? And that's what 65 is asking you to prove. It's asking you to prove that once you map those two things, you get a complete map of the whole DN, right? That's the only way you can map DN homomorphically into something, or isomorphic. I forget if it's isomorphism, it's probably isomorphism here.
Okay. Thank you, sir.
Or it's an automorph. Yeah, so it's automorphism, right? So you're actually mapping into DN itself, right? So, I mean, once you know that that's all there is to DN, right? It's just generated by these things. And, sorry, not F, RF, Rn minus 1F, right? So that's all there is to Dn, right? Then as soon as I take R and map it somewhere, right? I mean, I didn't even need to be mapping it into another DN. I could be mapping it to some other group and just preserving the group operations, right? That's a homomorphism. That's what next week we talk about some. I don't know, your book is kind of weird talking about isomorphisms before homomorphisms because it makes more sense to go the other way around, right? But here I'm mapping this thing somewhere into DN, right?
But you introduced homomorphisms in your videos already, though, so I understand what you're saying.
It makes more sense, right? So yeah, if I'm going to define a map from DN into any group, right? And all I need to do is say where phi of R, goes and where phi of F goes. Right, and then I need to make sure that the various rules make sense, right, to map the things, right. So in the case for DNs, right, you're going to be mapping. So R has to map to a rotation, and in this case, if you're wanting it to be an automorphism, so it's one-to-one and onto, it needs to map to a So I mean, R has to map to a rotation. It's got to map to something that generates this entire cyclic subgroup, right? And what did we just see a minute ago is to generate this entire cyclic subgroup, R has got to map to some RK. And what property does K have to have in order to generate that whole thing?
I just wrote that down. Is that has to do with?
That has to be less than N, but greater than 0.
Yeah, greater than 0, but less than N.
Like if RK is going to generate everything in R, right? Given what we just did, and we know that the size of this group is N.
Oh, it has to be.
Is that K
to be a divisor of N?
The GCD?
It has to be the GCD, right? I mean, so in order to get all of R back, K has to be 1. I mean, the GCD of R and K has to be 1, right?
Yeah.
So the GCD of R and K must be 1, right? Because we want to know that this is actually equal to that. But remember when we did that GCD computation, that means the GCD, because what is this thing here? It's going to be, I mean, in general, right? RK, I mean, let me just sort of, is also the same as RGCD of N and K. That's what we proved above, right?
Right.
Where this is the least possible thing that generates the group, right? So if I want that to be 1, then I need GCD of N and K to be 1, right? So if I'm going to get an automorphism, I need R to move to RK, where the GCD of K and N is equal to 1. Right, so I need that to happen. Okay, and then what has to happen with F? Can F? I think maybe F can just map to any. Yeah, I think F can map to any other flip, right? So it can map to any RIF for I element of, for I equal to 0, I guess NZN, right? Because remember, that's all that's up here. We got R, here it's like R to the 0, right? So 0 through -1. But so F can map to any of those, doesn't matter which one. R can only map to those things with, if I'm going to have it be 1-to-1 and onto, right? It's got to map to something whose GCD is equal to 1. All right. And then in the counting part of the problem, how many elements have GCD? So the set of all M in Zn. So the GCD of M and N equals 1, right? By Bezo's theorem, right, is the same as the set of all M and Zn, such that M inverse, the multiplicative M inverse, exists. Right, and that's the same as what the book calls UN. Right, later on in the course we'll call it UZN. Right, but that's UN, and the size of this UN, the set of things that are relatively prime, the size of UN is equal to this thing called the Euler-Toshin function in. Right, so all those things. Right, so now just in terms of counting, right, I needed to map R to RK, where K is in UN. So there are UN many ways of doing that, right? And I can map F to any of these N many things, right? And so how many ways can I do this all together, right? There are UN many ways of doing that and N many ways of doing that. Right, so altogether there are that many automorphisms, which is what the problem asks you to show, right? So the main thing here is recognizing that Dn has this form, right? So that you can see that everything's determined by where you send R and where you send F, right? That's sort of the, and then you just have to think, now we have to think about this sort of thing here. If I'm going to get all of the R back, if I'm going to get the entire, this entire cyclic subgroup back, then K has to be relatively prime to N. Right?
I know it's past time, Dr. K, but I have a question because every time that I was getting to the D initially last week or 2 weeks ago, I don't know how long we've been in this class yet, I was going back to the Cayley tables and trying to generate it through the Cayley tables. Is this the short version of not having to worry about creating a Cayley table to understand what's mapping to what? Am I bottling too much stuff into one thing?
I mean, the Cayley table's okay, but it's good to get a feel for what you're doing. But you can't, if you're gonna argue for Dn in general for an arbitrary n, right? You really need a more algebraic approach to it, right? You need to have a more algebraic way of thinking about it. And I really
use the algorithm, the division algorithm, and we use a division algorithm, the GCD, and we use Bezoid and all of that together to get all of that done, right? That's how that all comes together.
I mean, that was coming in to deal with the cyclic group part of it, right? But with the Dn, right, the main thing is thinking of Dn in this way, where it's generated by a single rotation, a single reflection, right, together with these relations. And I think it's a good exercise just to play with these relations and try reducing. By the way, anyone who needs to leave can leave, right? I mean, let me just.
I just want to be transparent and say I haven't read chapter 6 yet. So by just what I've read from watching your videos and what you've shown, this is going to give me a better understanding when I'm reading chapter 6. It's going to clear it up for me.
I mean, there's a lot of things in chapter 6, but I think for understanding Dn, I mean, don't get fixated on one little thing. Like, don't get fixated on just Dn. There's a lot of material here, right? Yeah. Dn's just a good example of a group to have. I mean, Zns are a good example. They're the cyclic groups, right? They're a good canonical example. Dn is a great, first of all, it's got a very sort of physical meaning in terms of rotating things, right? So it's got a nice geometric meaning. But it's also a very first example of a non-abelian group, right? That's sort of not just functions or something, right? So I mean, you're building up in some sense just some collections of groups, Zn, Dn, S, maybe Sn if you want to write it that way, the even part, An, right? So you're building up a kind of list of groups you know about, right? So that as we go on, we can do more and more stuff with these groups, right? But in terms of understanding DN, I think the best way to understand DN is in this sort of 2 generators, and then these 3 relations. I mean, actually, the way people do it is they just write the relations like this. Where implicitly this means that Rn equals E, F squared equals E, and Rf squared equals E. You don't even write the equal something. You just usually write the things that go on the left-hand side. But it's good exercise, pick your favorite D16, right? And just try using these rules to do some calculations of some crazy, like, R12, F3, R6, F, R minus 4, right? Reduce that down to something of the form RIF, where I is between, 0 and 16, right? Just for some practice, right? Practice using those rules. You'll get the feel for it pretty quick, I think.
Okay. Thank you, Dr. K. I appreciate it.
Mm-hmm. Okay, any other last minute questions? Okay, all right, good. Everybody come with your 2 things for next week too. I'll try to call in some different people next week. All right.
Dr. K, is it okay if I stay on with you for a second to talk about the homework from last week?
You can do that. I was going to say the other thing is when you choose your DQs, if there's something you're struggling with, choose that DQ, right? So we can have that discussion, during the week. Okay.
Okay, thank you, Dr. K. Good night.
Yep. Okay, yeah, go ahead, Caitlin. Wait, oh, it was you, Cassandra. I thought it was Caitlin. Sorry.
Yeah, okay. It was me. Sorry. So I wanted to first. I saw that you wanted me to explain how I did. Let me look which one it was. It was it was from chapter 0 or.
Oh, I remember. You pulled out the silo theorems and stuff, right?
Well, what I did for it was for the Calais group, I did not know what D3 was. So I went to ChatGPT and I said, what is D3? And it gave me the ER, R squared, S, R, S. Hold on, my tablet's mixed up. And then I put that in the table and I just did the multiplication of the top and the side based on what I had for D3. And then when I looked back through it, that's when I used the information that I found in it to say hey, there's that mix up where the
maybe I'm thinking about maybe I'm thinking about the wrong. Hold on, maybe I'm thinking about the wrong thing. Let me go back and look at it.
It was the Calais table. I'm trying to pull it up to see what. Hold on, because I couldn't get the format right, so it didn't look right.
Sorry, but Cassandra, what are we?
For the homework.
Yeah. Okay. Yeah. Okay. Good.
I'm trying to find
good.
what question it was. It was chapter 1, number 2.
The whole thing has some This is yours, right? Can you see that? Oh, did I stop sharing?
Hold on, I think you stopped.
Okay, let me get this. Right, this is yours, right?
Yeah, that's mine. I put the questions in bold and then the answers. Yeah.
Okay, but you see, let me
make
this bigger. I'm not even sure you can see it.
Yes.
I mean, you've got all this stuff.
I was having issues with formatting on that one and on 3 others, and they were all the ones you looked at because that's my luck. And I couldn't get the format to work right, and I objectively I know that moving forward I need to just do it handwritten for those that I can't get to format right.
So what are you using?
Yeah, and the HackMD is what I used for that one.
So I mean, you want to open it up and I can show you real quick how to fix a couple of these things just to see what's going on, or you want to? Yeah, can you share your screen or?
Oh, I can't share them on my tablet.
Or the other thing you could do is share it with me.
I can do that.
Editor. So maybe you can get the
That was
link.
like, I feel like the whole reason that I got my points knocked on the other two was because the format made it understandably very hard to read. Because
well, not only that, but it looks like it's being copied out of something. And like I've said before, I have to just be careful about people just copying stuff out of AIs or something, right? So that's sort of the.
No, trust me, I do understand. I didn't copy from anything. I did, what was it? The number 9 to, not 29, the one you did from number 229.
Can you, if you can share it with me where I can.
I'm sharing it now.
Edit, and can you do that? Can you send me the link in the messages here?
Yeah, that should let you in.
Oh, there
let me know
okay.
if it doesn't for some reason.
It's not letting me. So look, watch the permissions. So
into edit mode.
You have to make it public. Hold on, let me go to mine and see. Like here's your main sheet, right? So share, you have to share it up here.
Yeah.
Should I reload it?
Go on to publish. Oh, I didn't have it published.
Okay, does that change the link, or should I try again?
No, this should be good. Let me.
It's still saying forbidden here.
Okay, I just published it. Try. It doesn't look it changed the link.
There we go. There we go. There we go.
Okay.
There we go. So okay, so let me do it like this. So, well, okay, so there's all sorts of fun things to say here. I could talk to you about LaTeX a long time, right?
I've found some cheat sheets that I've been using to get slightly better, but I could not, for the life of me, figure out how to make the table look correct. That was a big one. And then I tried a good 20 minutes on the mess up print where it was just making everything superscript for some reason.
Okay, so
and I gave up. If I'm being honest.
You know what? Maybe instead of doing this right now, because it's kind of late, would you like to schedule a meeting and we can? So right now I still don't have edit access.
Oh my goodness. Okay. Yeah, we can do that. That's fine.
So let's see. If you're going to share it with me to edit.
I swear I did. It said edit mode, and I saved it before I copied it over.
You see where I'm clicking on the share thing?
Oh, the right is showing only me. Okay.
And unfortunately, I think you probably have to share it with everyone, not just me. The way it works, right?
But I see where I didn't fix that. All right. You should be good
now. Now I can edit it. Okay. So so I will say that to make a table is a little bit of a pain, right?
Which I was learning very quickly, and I was just praying it wasn't one of the ones you picked, and of course, luck of the draw.
So to make a table, you have to put some labels. And then you have to put some little things that sort of tell it how to space it, right? And that's and then I can start putting stuff in here, right?
Got it.
So there's some stuff I can put in there, right? And you got to use these little up and down lines, right, along the way in order to do that.
To space it out. I knew about the lines, but I didn't know I had to put the labels in, and that's where I was getting confused.
You can leave them
blank.
That's
why that first row came out like that, and then it went weird.
You can leave them blank, but that sort of basic structure has to be there. And
Gotcha.
then you can start filling in the stuff down here, right?
Okay.
So that's a thing, right? Let's see where we're having some problems with the
it
subscripts.
It was the one from number 2 that you tried to look at, because when I finished it and I went back and I compared I compared my work to your solutions before I turned it in, and I had I think my dots in a different space, and then
there it is, right here.
I formatted it more like the one that you would put into your solution key, because I was worried that having my dots in a different spot would mess it up somehow.
So let's see. Yeah, let me see what's going on here. So we've got this. See, the reason this is looking weird is because you never finished it off as a math formula. but now it's too long, right? And so here's
I need to break it up into parts.
Well, so here's the thing that let me try to see what I think maybe this will work. I'm not sure if this will work or not. Actually, let me show you what I do. When I want to make a longer one, I use this align.
Mm-hmm.
And it's got to start with an end align, begin align and end align. And then you're sort of, the little and symbol is like where things are going to align at. Okay.
Okay.
And let's say that I want to break it here. So if I'm going to break it.
Equal signs.
Yeah, if I'm going to break it, I'm going to put a double thing like that. And then I got to put another and symbol. Right. And you see how it does that, right?
No, that's awesome.
If I want to break it again here, say, right.
That was one of the most annoying things when I was typing it up, is because I wasn't able, I like to do that kind of spacing on my work, and I couldn't get it to space that way. So that would literally fit, because that's how I like to space things when I work out my problems.
So see, like awesome. Here you,
because like you see, I'm doing it in the code myself.
Yeah, no, I mean, learning LaTeX is good, but it does take some effort.
It doesn't transfer. So that's awesome, because now it'll transfer that way.
Yeah, in here, can you see like where I am there? So if I get rid of that, you should put like all the math in the math thing, but then this won't show up. So you want to do it like that.
That was the problem I was running into. I got to put the slash in front, and then that would work.
And then see, it looks like that, which is so much better.
Yeah.
Right. And
no, that really is. No, that was. And it was completely my fault. I waited until a little last minute, and then I just ran out of time to stop messing with it. And I tried putting the dollar signs in like 20 different spots, and then I was like, okay, we're done.
Yeah. So I would say, if you're not working right at last minute,
I know last week was a week. I'm so sorry.
You send me some messages or something, say I'm trying to type this, right?
And it's not.
And I would like to look at, but once you get the hang of it a little bit, you'll get the hang of it. It just takes some practice, right? It's
yeah, no, absolutely. Trust me, I'm so sorry that it messed up when you're trying to look at it, because
it was definitely hard to read. Yeah.
The second I saw the ones you picked, I was like, oh, that's not going to be a good grade, because those were like 3 of the 4 that I couldn't get to format any kind of way.
Okay, well, let's see.
And so they just came out a mess.
Okay, let me look at yours. Let me see what I actually said. Maybe I'll give you some points back, because part of what I was worried about is just how are you doing this, right? And I think I even think I said that if you talk to me, I'll give you some points back. So let me just see what I did.
Yeah, for the Kylase table, that was why that was the first one I wanted to talk about, because that's the only one that you said for sure I could get some points back if I could explain how I did it. And like I did use AI to figure out what D3 was, but from there I looked at the Kylase table in our book and based it on like the same steps in math there.
Yeah, I mean, yeah, it should be clear that I don't mind you using it. It's just I don't want you copying from it. And the way it was looking, it wasn't clear to me. Actually, let me pull this up so I'm not. I probably shouldn't show everybody. Great.
I can close my eyes for a second.
I'm just trying to remember what I did. Cassandra, I see. Okay.
No, I do have, and this is something that I got into with some other classes before that I need to get better at. When I start rushing my schoolwork, I forget to put in the little things that explains my in-between steps, and I understand it gets very just step. So like it's not the first time I've gotten that feedback that I need to explain more in words as I go, so it feels less like I'm copy pasting, because in all honesty, I'm just putting down the work part and I'm skipping the explanations, and that I will be better at that this week, I promise, to make it fit better and easier to process what I'm doing.
So I'm still going to say in part, in 45, I still don't see a full argument for that.
I don't think I had the full argument for 45. I know I had the answer for part B, but I didn't do the argument, and that was me on time. So like I know I'm not going to get those points back.
I will add
just my time.
So I'll add 7 points back. 7 points back would be everything, right? Okay.
Thank you.
It was worth it.
Makes me feel much better.
Okay. Good. All right. Yep. Yeah. Anytime, talk to me about the homework. Yeah. If once it's graded, you can always say, hey, I think, same with the exams too, right? I mean, because it's not easy to grade, right? And sometimes I'm having to try to guess at what people are doing, and it's it can be quite hard.
There's so many ways to do it.
There's so many ways, and sometimes students do things like use something that sounds true, and that's the reason they're doing it, because it sounds good. And I will, in all honesty, I have no idea whether it's true or not. And sometimes I can spend like a week trying to figure out whether or not the thing they claimed was true.
Yeah.
Right. So at some point I just have to say, this might be true, but you didn't show it. Right. So
no, completely understand. Thank you so much.
All right. Talk to you later. Bye-bye.
Bye.